So chapter 6 is all about exponential and logarithmic functions. Some Algebra 2 teachers get to it near the end of the school year, some don't. So you may have seen it, I don't know for sure. So we're going to assume maybe you've never seen it before, and we'll do as much as we can together, okay? Now, for exponential and logarithmic functions, there are lots of business applications and biology. Those are the two most common applications you're going to see. You'll see up on the screen here, there is a picture of E. coli bacteria. When in the height of COVID, when COVID was starting, a lot of models, it looked very exponential in the way it was growing initially. So when you saw those charts really spike up there, when COVID happened, it was an exponential looking kind of growth. So you will see a lot of biological applications, but there's also a lot of business applications. So you'll see both things as we go through the chapter. 6.1 is about exponential functions. I want you to see what they are, how you use them, how you graph them, how you see some applications of them. So there's some terminology you need to know. Exponential growth is an increase based on a constant multiplicative rate of change. So if the virus was doubling every 4 days, that's what it means by that 2 is that multiplicative rate of change. An exponential decay is when it starts coming back down. So if it is decreasing by a constant multiplicative rate of change, maybe it is the numbers are half of what they were. Maybe you have a bacteria in a petri dish and you're looking at the population and you add some antibiotics to it and the population decreases. That's a decay. Now the equation that you need for an exponential decay is f of x equals a times b to the x. This is 6.1.
Okay.
So the equation you need is f of x equals a times b to the x. Now it will be a growth if both a is positive and b is bigger than 1. It is a decay if a is positive but b is a fraction between 0 and 1, so a proper fraction, or a decimal between 0 and 1. A is the initial value, the initial starting amount. So if it is a bacteria, how many bacteria did you have in the petri dish? The base is the multiplicative rate of change. So your base is the thing that is multiplying again and again and again. And you'll notice that our variable, so this is a function of x, our variable is up there in the power. Now, this is the most simple kind of apparent form. This x could be a function of x, so it could be x plus 2, x minus 7, 2x minus 4. So this could be a function of x. So this is the most basic kind of parent function. So I just want to kind of show you an example of what a linear growth would look like versus an exponential growth. So look at our equations here. So this one is exponential, and this one is linear. Well, if we have y equals 2 to the x, it has a y-intercept of 0, and then the slope is up 2 over 1, up 2 over 1. You'll notice that. And then this is our exponential. If you plug in 0, you get 1. If you plug in 1, you get 2. And you plug in 4, or 2, you get 4, and so on. So that's those charts. Look at the difference here. If you plug in 6 into our exponential function, you get 64. If you plug in 6 into our linear function, you get 12. So there's only one little patch here where our linear function is higher than our exponential. And then most of the time, our exponential function would be much, much higher than our linear function. So if something is growing exponentially, it is growing much quicker than a linear function would grow. And the same thing for a decay. So for a decay function, it's going to go down a little bit quicker than our linear function that has like a negative slope. So let's practice graphing one of these. So we've got this function that's a very basic parent one, f of x equals 2 to the x. And let's remind you about some things about functions. For functions, or for exponents, if you have 2 to the negative 2, let's remember what that means. The negative takes the reciprocal of what you have. So this is really 1/2 squared. And then that 2 still squares it. So the negative's job is to find the reciprocal, and the 2's job is to square it. So that would be 1/4. 2 to the negative 1 would be 1/2. Now, remember what 2 to the 0 is. Anything to the 0 power is always 1.
Could you explain it one more time how it's going to work?
A negative exponent is going to take the reciprocal of whatever it's touching. So the reciprocal of 2, since it's 2 over 1, is 1 over 2. And then the 2 is going to square it. The negative's job is to take the reciprocal. The 2's job is to square it. Okay, so remember negative exponents. The negative's job is to take the reciprocal. The power's job is to take it to that power. So negative 3 would be 1/8. Negative 4 would be 1/16. And then if you look at 2 to the first, that's just 2. And 2 to the second is 4. You see these are the reciprocals. Negative exponents are reciprocals. Now, what's interesting about this function is it has what's called a horizontal asymptote along the x-axis. So we are always going to include on every single one of these graphs, we're going to include a horizontal asymptote. Now, it will always be 0 unless we have like a +1 or a -1, then it moves that up or down. So only if we have some kind of something added on over here would we have a change in our horizontal asymptote. And now let's plot our points. So at -2, we are up at 1/4. So just get real close if you can. At -1, we're at 1/2. At 0, we're at 1. At 1, we're at 2. And at 2, we're at 4. Now, this end is going to forever and ever get closer. Now, we can't draw that. I mean, we don't have physically, we can't. So just get close and kind of skim across there. And then this one's going to get higher and higher and higher. And that's the essence of what every exponential growth problem is going to look like. So what's the domain? Well, the domain are any x that we want. There will never be any restriction. It will always be, for an exponential function, any value we want to plug in, we're allowed to plug in. But there is a range restriction. In this case, the horizontal asymptote stops it. So the y, in this case, will always go from 0 to infinity. And the 0 has an almost 0, a parenthesis. So that means that we're almost at 0, but we can keep going as high as we want. Now, what's interesting about the end behavior here is one of the ends is always going to go to plus or minus infinity, and one of the ends is always going to head to the horizontal asymptote. And it depends if it's a growth or a decay as to which goes to which. Now, remember, left is always x going to negative infinity. Right is always x is going to positive infinity. And let's see what's the y doing. Well, for the left end here, the y is heading to the horizontal asymptote height of 0. So the left end, the y is heading to 0. The right end is this end here. It is heading to a height of infinity. So this means going up. This means it's going to the horizontal asymptote. Left and right never changes. X goes to negative infinity is always left. X goes to positive infinity is always right. Let's talk about the intercepts. There are times where we won't have an x-intercept for these. So the x-intercept is where the function equals 0, which won't happen. So there is none. You're only going to have an x-intercept is if we pick that function up and move it up or down. If we move it down, it'll have an x-intercept. But in this case, we don't have that. What is the y-intercept? Well, we already did that. We plugged in 0 earlier, and we got 1. So the y-intercept is 1. It's this point right here. This point right here. That's your y-intercept. If it's a growth, it will always be increasing. If it's a decay, it will always be decreasing. So as our x goes from negative infinity to positive infinity, look at our little math bug. Our y is increasing. Our y is going uphill. That is why it's called a growth. The function is growing over time. As our x goes from negative infinity to y infinity, our y is increasing. Our math bug, as it goes to the right, is going up. Any questions about the basic graphs? Now we're going to talk about transforming them more, but for now, does everybody understand that basic kind of graph? Okay. So let's look at determining if something is an exponential function. So remember, our exponential function looks like this. But this can actually be some function of x. Now there are some restrictions. That has to be positive. And this can be any real number. So it just can be any real number. But b has to be a positive number. Cannot be negative. A can be whatever you want but 0. But b has to be positive. So if we look, we got a positive base. We have a function of x up there. That's a yes. This one is wrong because our base is an x and not a number. That's a no. We already know what that is. That's a power function. That's a cubic. That's not an exponential. Take a look at h. This is a positive number. That's a power of x. That's a yes. That fits all the criteria. Let's look at j of x. This is negative, so that's automatically a no. That's called an oscillating function. That is not the function that we would want. Because if x is a positive power, or an even power, it becomes a positive. If it's an odd power, it becomes a negative. It keeps oscillating back and forth. So that's just kind of, just identifying when you look at it, that's an exponential. You have a question? Yes.
Is A always going to be in parentheses?
No. Sometimes you'll see it written like, 5 times 2 to the x plus 4. But they'll put a distinctive little dot, or they'll do this. I've seen it written both ways. It just has to be separated from the base. It just has to be separate from the base. Or in this case, like we don't have one, the A is 1. So that if you put, what is the A for both of those, they happen to be 1s. But any other questions about that one? Let's look at example 2. Let's practice plugging in to an exponential function. You have to be careful when you put these into a calculator. You just have to, because the calculator is only as smart as the person that enters the information that it knows what it's doing. So you got to be careful. So let's use f function to plug in 2. So that's 5 times 3 to the 2 plus 1. Now, if you recall, please excuse my dear Aunt Sally, P is parentheses or kind of things that are grouped together. E is exponents. And exponents is what we're talking about. We're talking about exponential functions. So when you do this, that is really 3 to the third. Really, that means 5 times 3 times 3 times 3. The 5 is not included in that. So I would suggest putting into your calculator 3 to the third, getting 27, and then multiplying by 5. So just be careful how you enter these into a calculator. And if you entered this one the way that it sits into a calculator, most calculators, you're going to have to group that together in a parenthesis. So just watch how you enter it, okay? Okay, now let's plug in -1. So -1 plus 1 is 0. Now remember, anything to the 0 power is 1. So that's going to be 5 times 1, or 5. So, you know, when you're next time you use one of those red calculators, put that into the calculator. Make sure you're getting 135 for the first one and 5 for the second one. Then you'll know that you're entering them correctly, because it's very easy to mess up how you enter these into a calculator. Especially one here that has a decimal in it. Let's do C. We're plugging in G of 3. We're plugging in 3. So we're going to do 3 minus 5 first. We're going to get -2. Now, let's think about what -2 is. -2 is the reciprocal of 1.2, then squared. Now, let's talk about the number 1.2. 1.2 is 12 tenths. Isn't the decimal there tenths? So that's 12 tenths, which is the same as 6 over 5. And you don't have to do this. If you have a calculator, you have a calculator. But it's going to be more accurate if we do 6 over 5 to the -2. Why? Well, because we can control that. And we don't have to round it. So fractions are usually actually more helpful in this context than before, because we can do the negative, which job on the negative is to flip it, make it the reciprocal. So that's 5 over 6. Now I've used the negative. Now I can do the squared, which is just square the top and square the bottom. You might notice that I haven't touched the 8 yet, because the 8 is not, it's not involved. Now, 8 and 36 are both divisible by 4, so we can do a little reducing. And so we get 50 over 9. And that's the exact answer. 50 over 9 is our exact answer. And I like exact answers if we could. If you put that into a calculator, 50 divided by 9 is 5.555555555 forever and ever and ever. Little trick that I showed my last period class that I think is kind of neat. 1's repeating forever and ever and ever is 1/9. 2's repeating forever and ever is 2/9. 5's repeating forever and ever and ever is 5/9. 3's repeating forever and ever is 3/9. This is what's interesting. If you have 2 digits repeating forever and ever and ever, that's over 99. If you have 3 digits repeating forever and ever and ever, you put it over 999. And one day I can show you why, but it is a pattern, and it's really kind of cool. So if you saw this on a calculator, it's going to say 5.55555, which is 5 and 5/9, technically.
So we have to put it in the next one?
No, I like 50 over 9. I was just showing you. Kind of neat. Okay, so anybody have any questions about example 2? That was just a little extra piece of information. Okay, so there are lots of applications for this stuff. Exponential problems occur in biology a lot. When it comes to viruses, we saw it with COVID and all those charts that we saw that it was growing exponentially. We see exponential decay in populations of like animals that are going extinct. We see it in bacteria when we add antibiotics into the mix, and it kills the bacteria, hopefully exponentially. But it is a real thing. And so I want you to have some applications. And so our first equation I want you to know is the exponential growth. P is the initial amount, the R is the rate of increase, and T is the time elapsed. If R is negative, that would be an exponential decay. So if we had, a petri dish filled with bacteria and we added antibiotics in and the bacteria started to decay, the R would be negative. So if they make sure they're telling you that the population is increasing, use a positive. If they say that population is decreasing, use a negative. So let's do a problem. So there's the equation from the other page, A equals P times 1 plus R to the T. So you want to write that down. In 2013, India had a population of 1.25 billion. The annual growth rate is 1.2%. What would the population be expected to be in 2031? Well, let's write down everything we know. So the P is 1.25 billion. Let's add all the zeros here. The R is a growth rate, so it's going to be a positive 1.2%. But please get in the habit of changing that to its decimal equivalent. So 1.2%, move the decimal over 2 places. Percent means per 100. You can divide by 100 or move it to the left 2 places. You get 0.012. You always want to use the decimal equivalent of the rate. The T is how many years has it gone past. So it's going to be 2031 minus 2013. Isn't that 18 years? 18 years. And we're looking for the amount. Remember that A is your final population, your final amount. So let's plop everything into the equation. So we get 1.25 billion. And then 1 plus 0.012 to a power of 18. Now again, I would be very mindful of how you put this into a calculator. So I'm going to do the parentheses first. Get 1.012. I'm going to take that to the 18th. And then for, these are humans, people. For any kind of biological creature, round to the nearest whole number. Okay, just round to the nearest whole number. So our amount is 1,549,384,611 people. And if it's a real life application, make sure you put units on it or describe what the heck that number means. So in 2031, we should expect there to be 1.5 billion people, which is a lot. And that's only 1.2% change. And I think the growth rate of the population of the world is actually higher than that, which is not a good thing. Are we good for example 3? Okay. Let's look at example 4. So it says, in 2006, there were 80 deer in the park. By 2012, the population had grown to 180 deer. Find an equation to model the growth of the deer population over time. So we're expecting that we're going to get to use that exponential growth equation that we saw before, a equals p times 1 plus r to the t. So to find the equation that will model it, we need to know p, which is our initial amount, and r, which is our rate of increase. So we have to find those two things. We just want the t to be our only thing that we could use in this. So what do we know? Well, our initial amount was given to us as 80 deer. So usually they're going to tell you the initial amount in the park, or in the first year of the counting up the deer in the park, there were 80. So we know that part. So let's put that into the equation, and then we don't have to worry about it now anymore. The p is always going to be 80. But now we have to figure out what's the r. So let's think about the information that we haven't used. 6 years later, we had 180 deer in the park. So when our time was 6, our final amount in the park was 180. So we can solve for r by plugging those values into that equation. So this is 180 equals 80 times 1 plus r to the 6th power. Now, that is an algebraic equation that you should know how to solve. Well, if something is stuck, whether it's in a radical or in the opposite of power, you want to isolate that. So this 80 needs to be removed. So how do we remove it? Well, we're going to divide it off. And you pretty much go through this same pattern every time. 180 over 80 is the same as 18 over 8, which is the same as 9 over 4. So let's make that 9 over 4. I just reduce it as much as I can. And usually fractions are a little more helpful for this. Now this next phase, you're going to have to use a calculator. The thing that's going to get rid of a power of 6 is the 6th root. Now if you've never used that on a calculator here, let me show you how I would use that on like one of those red calculators in the back of the room. Okay? So you would put the 6 in first, then you would hit the second button, then you would hit the caret, because that's the opposite of a power, is a radical, and then you would stick in a parenthesis 9 divided by 4. Okay, so that's how you would enter it into the calculator. So you put in the power, the index, the 6 first, then you second the caret button, and then you should see a little radical with an X pop up. This will make this little button pop up. And then you stick in parentheses 9 divided by 4. Now you have to use the parentheses or it'll just take the 6th root of the first number. So you have to be smarter than the calculator. You have to enter it in correctly or it's not going to work. And when you do that, you want to leave that decimal in with all, as much as you can, or write down 1,000,000 trillion decimal places. And you get that 1.144714243 is 1 plus r. Okay. So now we know our r, if we just subtract 1 from both sides. Let's go 4 decimal places. I think that should be enough. Is 0.1447. So now we just got to replace it in here, and we have an equation that would model the growth of the deer population over time since 2006. So our equation, our final answer is A equals 80 times 1 plus 0.1447, or you could just write 1.1447, this value, to a power of 2. And that's your answer right there. We now have an equation for that particular park that we were looking at the deer in.
Did you put like the 6 years where the t is, or does the t have to be there?
The model would be with that I could be able to plug in any t I wanted. So the t, it should work if I put in 6, but I also want it to, if I wanted to say, well, what would it be now in 2023? So I should be able to plug in 17, and I should be able to find out how many deer there should be in the park now. You know what I mean? So you want it to leave a generic t in there so you can plug in whatever you want. Any other questions? Yes.
I do have a question.
Sure.
So when you did the 6
Uh-huh.
plus 180,
Uh-huh.
couldn't you just do 180 minus 80 and then divide by 6? Would that still work? Doing it that way instead of doing the proportion?
Tell me again what you wanted to do.
So like subtract the 80, the initial amount from the 180, and then divide by 6, which is the time.
Unfortunately, no, because if it was a linear growth, you would do exactly what you just said. The problem is it is an exponential growth, and because for exponential growth, it is multiplying by itself again and again. The thing that's going to undo that is a radical, not a division. So you have to unfortunately do that. So yes, if it said a linear decay or a linear growth, you would do what you just said. But since it's exponential, you would have to divide it off and then use a radical. Any other questions? Okay. Now, that was a biological sort of application. Another application would be investments. Whether you had a savings account or if you had a loan for a house or for a car, they're going to use a compound interest formula that you see here. Now, the only difference in the formula that we saw before and the formula that you see here is this n. The n is the only difference. P is still the starting amount, R is still the rate, T is still the time, but this n is an addition. And it is the number of times per year that they're going to compound your interest. So if they compound your interest monthly, it's going to be 12. Daily, it's going to be 365. So how many of those things occur in a year's time? The most common one is monthly. That's going to be 12. Weekly, 52. Daily, 365. Quarterly, it's going to be 4. Those are the most common. So the only difference in this formula is, in the last formula, is the n. In the last formula, the n is technically 1. You could use this formula for your exponential growth and just use an n of 1. Yearly would be 1. So it's how many times that thing occurs in a year's time. Most savings accounts, if they're going to give you interest, would be a monthly, so that'd be 12. For some credit cards, they'll do a daily interest, and that because that gains them more interest. So you always want to read that fine print. Most loans, whether it's cars or houses, are interest compounded monthly. So it's usually 12. There are some exceptions. But these are just kind of logical. Think of how many times does that occur in a year's time. So let's look at an example. So there's the formula from the last page. I put it in there in the corner. It says we're going to invest $3,000 in an account paying 3% interest compounded quarterly. How much is in the account after 10 years? Well, let's write down everything we know. The initial amount is $3,000. The rate is 3%, but we're going to change that into its decimal equivalent by dividing by 100, 0.03. Move the decimal 2 places to the left. The time is going to be 10 years. The number of times per year that they're going to do interest, they said quarterly, which means 4 times a year. 4 quarters in a dollar, 4 quarters in a year. And then the thing we're looking for is the final amount. So let's plop that into the formula. So here we get 3,000. 1 plus 0.03 divided by 4. And then 4 times 10. Now, it can be very easy if you enter that wrong into the calculator to mess things up. So here I'm going to kind of give you some hints. So the first thing I'm going to do is I'm going to ignore the 3,000. I'm going to do this. What is 1 plus 0.03 divided by 4? Your calculator will understand that and give you a nice decimal. If it stops, perfect. If it doesn't, I would at least show 4 decimals, probably more. If I was doing it, I might even try to leave that yucky decimal in the calculator. But if it ends like this one, that's great for us. And then the power, I would actually do that separately as well. 4 times 10 is 40. Now, let's think of order of operations. We would next do this, because order of operations, exponents comes before multiplication. So if we do 1.0075 to the 40th power, get an answer, and then don't change the calculator, don't do anything, and then hit times 3,000, that's the safest way to enter it into your calculator. And you should get, now this is money. Money applications, put your dollar symbol, and then round to the nearest penny, which is 2 decimal places, or the hundredths place. So that was $4,045.05. Round to the nearest penny. That means that our interest that we gained in the account, if you take off the $3,000 we initially invested, we made $1,045.05. They say the best time for you to invest money is now. Every time you get paid, whether you're working at McDonald's or you're working at a nursing home or wherever you're working, from the time you are this age, if you start putting 10 bucks from a pay or 20 bucks for a pay, by the time you retire, it's amazing how much interest you're going to gain. Even right now, you won't get 3%. Most savings accounts in this country right now are getting 0.5%, 1%. Savings accounts right now are bad. But over long term, even that 0.5% would gain you quite a bit of money. Okay. Any questions about example 5? Okay. Let's talk about another biological kind of application, continuous growth and decay. And the word here that you want to know is different than the other equations, is that word continuous. If you see that word continuous, you're going to use what I call the PERT formula. It's just a quick, silly way for me to remember what it is. The continuous tells me that we are going to use the PERT formula. Now, the P and the R and the T are the same from before. The P is your initial amount, the R is your rate, the T is your time. But like before, in any kind of biological application, if your R is positive, it's going to be a rate of growth. If your R is negative, that means it's decaying over time. So we've just added antibiotics into a petri dish of bacteria. The bacteria is going to decay, hopefully, if the antibiotic is working. Okay. Here we've added something different that you might not have seen much of before. There is a number like pi that's irrational. Most calculators have a button on our calculator here, the e to the x button. So you just have to hit second, then ln would get this value to come up. 2.71828 is just like our, pi is 3.14159, that number. E is just an irrational number that comes up a lot in biological and in business applications. And so you will see, if you ever see an E, you always want to use either that button or remember that it's approximately 2.71828. Now it keeps going on and on and on forever and ever, and it never repeats or does anything lovely. But, okay. So let's just practice pulling that up into a calculator. So if you want to grab a red calculator, you can, just so you make sure you understand how to do it. If you're going to enter this into a calculator, and I want you to take it out, maybe let's go four decimal places. If you decide to enter into a calculator, what you want to hit on the calculator is you want to hit the second button, and then you want to hit the natural log. That's ln. The ln button, we're going to discuss logarithms at the end of, a few sections from now. So you would hit the second and the ln, and what pops up on your calculator is an E. This will pop up an E with a little caret next to it and a parenthesis. Okay? And then you want to enter in a 2. And then you're going to get a funky decimal. I mean, there's just no way around it. These, again, let's go 4 decimal places. That's approximately 7.3890. Well, if we round that up, that's actually a 1. Okay? So just make sure you understand where that button is on the calculator. You're going to need that. You could have also put into the calculator 2.71828. You could just enter that in manually. And then you put to the square, and you should also get that. Now, I understand that we might end up putting things a slightly different form. If you truncate it and stop that decimal, you might get a slightly different answer than I am. I'm going to understand that, and I'll just check that you should be close to what I have. Okay. So on the calculator, you can enter 2.71828 to a negative 0.5 power, or you can hit the second natural log and let E be generated on there on your own. Okay. So, or again, you can hit the E to the negative 0.5 if you use the natural log button. So, however you want to enter, it's fine by me. And because that negative flips it and then takes it to the half power, it's going to give us kind of an interesting result, because it's going to flip it and then square root it. And so if we take it out 4 decimal places, it's approximately 0.6065. And again, if you use the 2.71828, you might get a slightly different decimal than that, and I'll understand that. But make sure you either do this or you take that 2.71828 to whatever power. So some calculators, like especially if you use a calculator on your phone, I know that on an iPhone, if you turn your calculator to the side and get the full calculator, I think it is in there somewhere. But if you use the straight up and down on your phone, you're not going to find it either. Okay? So let's talk about an actual example, and we're probably going to stop at this example, but we'll see. Okay, these are actually pretty quick. So it says we have $1,000. We're going to invest at a 10% compounded continuously account. And how much would we have in a year's time? So our P is our starting amount. Our R is 10%. Written as a decimal is 0.10. And then our time is 1. What is our final amount in our account? Well, if you stick that stuff in the equation, it's 1,000 times e to a power of 0.10 times 1. Well, 0.10 times 1 is just 0.10. So it's just 1,000 times e to the 0.10 power. And we get, you have $1,105.17. So our interest we have gained is $105. Pretty good for just leaving your money alone, leaving it sit there for a year, and you gained $105. Okay. What time is this bell ring? Do we have like 2 minutes? Or do we have like 5? Well, we only have one example, so let's just get it done, and if the bell rings, I'll show it to you tomorrow. Okay, so this one's kind of interesting. We have radon, which is a radioactive element, and it decays 17.3% per day. If we start with 100 milligrams, how much is left after 3 days? Okay, and if we consider it a continuous rate of decay. So what do we know? Well, we know we're going to start with 100 milligrams. You'll notice that the rate said per day, and this was per days. Those, if they match, we can use the formula without any sort of changing it up. So our rate is 0.173. Since it's decaying, make sure you make it a negative. The time is 3 days. How much is left? And it should be a number less than the 100 milligrams if we did it right. So let's set it up. We get 100 times E to the negative 0.173. Let me say that right. Negative 0.173 times 3. I would get that number or put it in parentheses. I would probably round it to the nearest maybe 10th or 100th. If I don't specify, just give me an answer. And we get that there is 59.5 milligrams left. And if it is a unit of some sort, tell me the units. Tell me what your answer means. Now, if it says how much decayed, you would subtract from 100, but that's your final answer. Okay? And then your homework is right below. And it's actually a pretty quick assignment. Okay? There you go. Have a good one, guys.